Welcome everyone. Our topic is about another kind of user mode fuzzer towards iOS and macOS, which we name PESSR. It's designed for a kind of portable, extendable, and scriptable and seed reproducible mobile fuzzer. And this is our agenda. First, we will introduce our member, and then we will introduce our solution for PESSR fuzzing, including the fuzz strategy and the crash monitor and reproduce strategy and our further plan. And finally, we will introduce our hunt practice where our fuzzer.
Hi, I'm Ju. I work for Meituan. I have 6 years of experience in advanced street research. Now I focus on research about zero-day, N-day, and vulnerability. I have been working on using automatic systems to hunt advanced threats.
Hello again, I'm Moony. And usually I worked on the Windows platform for exploit and vulnerability hunt and the sandbox security analysis. And now I'm focusing on the mobile platform, including iOS and Android for vulnerability hunt and research. And this is our member.
My name is Lilang, and I have 3 years security experience on iOS and macOS vulnerability and malware detection.
Okay. Under the next part, we will introduce our PESSR solution in detail. And first of all, I will introduce the fuzzing tool in comparison to our different kind of fuzzing tools and according to different mentions. For example, the left one is for the Trinity, which is the open source syscall fuzzer in the user mode, and the AFL, the basic, the AFL, which is the famous code coverage based fuzzing system, and also the Triforce, or as well as color, which is another kind of code coverage based fuzzing system towards the kernel. And also the final one is our PESSR. We will compare different fuzzings according to different dimensions. For example, the platform, fuzzing interface, code coverage support, driven by support, and the reproduce strategy, and the portability according to the platform. As we know, Trinity is a typical old-fashioned system call fuzzer with different variations. With researchers configured the system call format, for example, the parameter type or the return type, it records and serializes every log of API context before call it. Researchers could only try to reproduce the crash by collecting the log, whereas the log review effort would be huge and reproduce by log would fail for complex scenarios. For example, if the API correlation is tight, so the reproduce will depend on the environment. So in these conditions, it's hard to reproduce. Another kind is the AFL, which is the which employs a novel type of compile time instruction and generic method. Sorry, and the Triforce is and the Triforce override the code coverage-based thinking of AFL, and it will extend the fuzzing targets into the kernel. And the final one is our PESSR. So, actually, we design our PESSR according platform. So we will try to wrap our fuzzing agent according the script, which is crossing platform. And also about the fuzzing interface, actually it can towards the use mode or the kernel mode both. Currently, our PESSR is not supported code coverage, but in the future plan, we will consider add the code coverage in our solution. And about the reproduction part, the PESSR is based on the seed. As we have mentioned before, using the seed strategy, it can save a lot of reproduction effort. Okay, this is our whole solution in detail. As we can see that is most composed by different parts. The main part is the fuzzer agent. The fuzzer agent is, you can consider it as an executor in the use mode, which will try to cause attack interface towards use mode or kernel mode. And the other part is for the crash monitor. The crash monitor will try to get the crash or harm information of your target process according whether your device is jailbreaked or non-jailbreaked. It has different strategy. And the other side, we can see that we will provide our secret server. Because our fuzz agent is wrapped by Python or Node.js, like script language, so we can easy to save our fuzzing strategy or fuzzing scenario in format of script, and we can put this all kind of scenarios as script in the server. And when the fuzz agent will try to run to cause attack surface, it will first load the fuzzing script or fuzzing scenario from the server and run locally. The other part is about the seed. Because the seed strategy has its own advantages in production. So for every kind of crash issues, we will get the corresponding unique and identified seed. So we can save the seed or the integer into the seed server for reproduction. Okay. About the fuzzing agent, the main function is try to trigger the fuzzing interface and reproduce the crashes. The key important framework, for example, the XPC, OurKit, or system call, or the system library, we can all wrap this kind of framework in the script. because it has no compile phase effort, so we can keep this kind of solution crowding platform. And also we will integrate our seed reproduction strategy in our fuzzing agent. Another side is the secret server. The secret server is mainly providing fuzzing script, updating and downloading. Researchers could configure the fuzz script towards fuzzing interface, or even update the script at runtime when the fuzz agent is running. So, okay, the crash monitor is responsible for detecting the crash event for fuzz agent. Actually, by design, after fuzz event, for example, the key slice leakage or information leakage could also be detected by monitor. For view of fuzzing target, it could be kernel module, for example, the XNU or kernel driver or the other kind of module in driver or kernel, or any use mode modules or processes, for example, the XPC or match service daemons. If the target service is jailbreak, the crash monitor could be deployed inside of the device because we have sufficient privilege to monitor the target process. Otherwise, the crash monitor is deployed outside of the device or host. And normally, the crash monitor could detect the device crash event with, for example, the iTunes protocol via your USB. Okay, so this server is mainly for collecting the fuzzing seed for reproduction because before the target device crashes. The main strategy for seed reproduction is that you can use one unique and identified integral value, for example, 4 bytes. According to specific procedural algorithm, you can use this kind of value to generate a sequence of data which is decided. And by this kind of seed, you can reproduce the reproduce the data exactly. Okay, this is a snapshot of our seed server. You can see that the left column is the ever crashed XPC services, which is a com.apple, and this one. And this is the script we have ever collected toward this kind of module here. So you can see that after running several minutes, we can get a lot of maybe hundreds of error crashes cases in our seed server. Oh, sorry. Okay, the other part is about the fuzzing strategy. So the first question is why we fuzzing in script, and the second is how we porting the script engine onto mobile devices such as iOS and Android. And also we will introduce how we wrapper the iOS or Mac framework. Okay, we can see that. Actually, for the fuzzing agent, there are different kind of implementation. For example, you can implement it using the native code, such as C or C++ or Swift or any other object-oriented language supported by Apple. And the other part is about script, such as JS or Python. And we will compare the different kind of implementation by different dimensions. For example, whether this kind of fuzzing agent is crossing is easy to port to different platform, and whether we can modify the fuzzing logic at runtime or not, and whether it needs the compile effort. And finally, we will choose the wrapper our fuzzing framework of iOS or Mac in format of a script. And actually, we have some research about this script wrapper solution on different platforms. For example, the Kiwi framework, Kiwi open source framework for iOS, and Kiwi Python for Android, and also the Node.js for both iOS and Android. And actually, we have also compared this kind of open source framework according to different dimensions. For example, whether this kind of framework need more privilege on the platform, or whether it will cost effort to porting different platforms, and which platform it supports. Actually, this is the snapshot of code pieces which we will binding the match message or XPC framework using Python. You can see that. This is the API or attack surfaces in framework of XPC. Send message XPC, create connection, and XPC handler, and also match message send and receive. Okay, this slide you will get the basic view of all the attack surfaces in both user mode and the kernel mode traditionally. And you can see that in the left column, the system APP with high privilege or XPC services, these are all user mode with high privilege. And the allocate driver, XNU kernel, and iBoot, which is the bootloader, these are in the kernel mode. There are many reasons to why we will choose this kind of API as attack service. For example, for system APPs, for example, Safari, or Apple Store, or iTunes, because potentially we could get the remote control exception vulnerability in this kind of system app. And for XPC services, because it's root or high privilege, and also it could be called from a low privilege app or sandbox apps. For the allocate driver, because many of the allocate drivers, such as the graphic, video, audio, and the other kind of drivers could be easily called from the sandbox. And the XNU is the kernel, which is cross-platform in both iOS and Mac OS. Okay, the other part is the fuzzing by emulation.
For a long time, our fuzz on our XPC server is based on iDevice, for example, iPad or iPhone. But in order to increase code coverage, we generally need to run a large number of cases. Due to the limited performance of the iDevice, our efficiency is not high. Efficiency must be improved. Only a large number of iDevice will be purchased. This is a big cost, and for most team, it should be a big challenge. So based on the iOS XPC server's mature file is actually the ARM instruction set. We boldly proposed the idea of replace a large number of iDevice with ARM service. But at present, a large ARM server, its price is very high. So we choose a low-cost ARM device. It is the Raspberry Pi. Then we use the Raspberry Pi cluster to construct the ARM device cluster, which is almost close to the current mainstream ARM server. In fact, there is already a similar open source project on GitHub. Darling is a translation layer that allows you to run unmodified Mac OS binaries on Linux. In its nature, it is similar to the Windows Wine project. He has implemented a dynamic loader that can load Mac OS EX and the runtime system library and framework implementation so to enable Mac OS EX to run and so on. Unfortunately, however, it can only support x86-based Metro, which runs on macOS. The next thing we need to do is to let Darling support ARM-based Metro. Based on low-cost custody consideration, our goal is to transplant them to Raspberry Pi. We call it Darling Pi in order to maintain the name continuity. But we just borrow his source and rebuild the code. Through the transplant, we have implemented a dynamic load that can load ROS X and runtime system library and framework implementations to enable iOS exe to function and so on. In fact, we only need to realize the Raspberry Pi to actual for system emulation emulation by QEMU. This is a quick and easy way. With this system, we further mature or even some fragment code which become easily. Any iOS XP server run independently under our Darling Pi and expose or attack the surface. We can use a large number of cases to fuzz it. And the code coverage is calculated by recording the core stack, and the new cases are generated by backtracking. After the design of such low-cost hardware emulator, we can run a large number of cases which save the cost and improve fuzz efficiency. As we would see, a good fuzzing activities should be extensible and portable, which should be implemented by a good architecture design and high code quality. It would reduce your much effort of fuzzing if the project is well designed improvement. Security researchers should build or share large scale or scenario POC toward the attack fuzzing interface. Some normal scenario POC would be complicated and usually is the United test case for video developers, and is beyond the knowledge scope of security research. The more scenario POC toward the attack interface you gain, the more possibility you would trigger vulnerability. Actually, the ever hunt hand or crash case would always interference your further hunting, because with high possibility, the ever crashed issue would happen again and again to interrupt your fuzzing. We recommend this key field which have caught crash be extracted and the whitelist filter automatically. For example, for XPC server bug hunt, the MSGID inter buffer is a good field for filter for XPC fuzzing.
Next, I will introduce some modules, including crash monitor strategy and reproduce strategy. And we also introduce our future plan to strengthen our tools. We all know that fuzzing on our system is a painful thing, especially on jailed device. However, luckily, they have already some excellent toolset implement the iTunes protocol, which can help us to communicate with the iDevice, such as live mobile device. Then we can use the iDevice's log to monitor the system log whether an XPC is crashed or exit. What's more, there are also some vulnerabilities such as kernel bugs. When we trigger them, they will create related diagnostics information in the crash report folder. So we can use the iDevice crash report tool to pull this information for monitoring fuzzing status. However, for jailbreak this system, we can get more privilege, so we can monitor the fuzzing status on device directly and use the socket mechanism to communicate between fuzzer and monitor the daemon. This is the practice for our monitor strategy. For monitor the target service status, and we monitor the process calls instead of one of its sub-process. What's more, we also add the system and service freeze signal into our fuzzing tools. Next, we will introduce the reproduce strategy. There are many interference factors to make crash reproduction harder, including rest condition, API cost correlation, and environment dependency. For example, if the vulnerability is triggered by a series of APIs which code in a specific order, it's difficult for us to determine which is the first API to cause this issue. There are also many methods to reproduce the crash. Here we list 4, including log, case film, crash dump, and seed. Mentioned before, we use the seed based on procedural random number generator with Mason twister algorithm to fuzz the targets. So for each fuzz circle, we can simply save those seeds in the server, and no need to save any middle status or data. After comparison, we can find that reproduced by seed only costs more storage and the speed is fast. What's more, it only spends a little effort than other methods. This is the implementation for client to communicate with server through socket mechanism. We use it for transfer. We use it for seed transfer during fuzzering. We only use the socket to transfer seeds, and as mentioned, seed is actually a 64-bit data, so network transmission speed is relatively not low compared to disk storage serialization. What's more, the seed server is hosted on the outside of running target, so we can easily redirect the traffic to any other server and ensure its stability. Another advantage for using socket is that we can deploy multi-fuzz agents with different server ports. Fuzzing server will create different folders to save corresponding data. We recommend you to record last N seeds for reproduction, and N should not be too small or too big, because if N is too small, the root cause seed causing target crash will be missed because the early exit delay from root cause trigger to final target crash. And N should not be too big because the most ODCs may not related to the current target crash. So it would be time consuming for reproduction. In this case, we recommend you to record bigger number NCs, for example, 10 Cs, and keep the last N subtract M details logs, for example, 2. In this way, the redundant AMCs make sure you could reproduce the crash, while the last N subtract M details logs can help you to verify the crash as soon as possible. This picture shows the last NC's logs. Next, we will talk about our future plan. We will integrate the code coverage feedback for our fuzzing tool, like AFL, Hugging Fuzz, kernel mode, and syscaller. And we all know nearly all of iOS and macOS drivers and framework library are closed source, and so our dynamic and static binary instrumentation is the alternative methods. What's more, we will also support the persistent mode like AFL. For those fuzzy interfaces which could not access to for linking or privilege or prevented by security policy check, we plan to attach them and hook related functions for fuzzing. Actually, this method have already proved practicable by HunkFuzz. What's more, in order to improve the quality of input data for fuzzer, symbolic execution will be introduced to get the input constraint. And there have been already some excellent open source tools for assembly symbolic execution, such as Unger. We have mentioned Darling Pay before. In practice, OS XPC service always need to interact with other XPC service. So we can simulate other XPC service to implement and communication with the target XPC service with Darling Pay, and fuzz them based on the simulation we mentioned before. Finally, we will disclose some hunting practice and tank interfaces. The tank interfaces mainly contain XPC daemon service and sandbox reachable kernel extensions. Here are the services got by Lilang launch CTL dump state command. These are service lists with their PID and exit code. This is the details information of found object server, including its port, active status, and other detailed information. This is a mutational match message body instance based on highlight seed. We can see that multi data are replaced by malformed ones. This is the vulnerability we hunt, and Apple have fixed it recently. We also submit some crash requests to ZDI, so we will wait them to fix later. Here we list the kernel extensions which can be reached directly through sandbox apps, including for our iPhone X, iPhone 7, and iPad Air.